So electromagnetic waves can pass through matter and through a vacuum. All travel at the same speed in the same medium, and that's 3.0 times 10 to the 8 meters per second in a vacuum. All are transverse, and the evidence for that is that they can be polarized. We'll have a quick look at what that means in class. It's not particularly important for the level 2 curriculum, but in order just to have evidence that actually electromagnetic waves are transverse, we kind of need to see that. Electromagnetic waves are all produced by moving charges. More specifically, they're produced by accelerating charges. For example, radio waves are produced by making electrons wiggle up and down in a transmitter aerial. This produces an oscillating electric and magnetic field that moves outwards. Electrons in your radio aerial are caused to oscillate at the same frequency. Your radio converts this alternating electric current into sound. Okay, and here's a little diagram. So basically we have a transmitter aerial that's going to cause the here let's change color here, which is going to cause electrons to oscillate up and down in here. As they oscillate, they cause a disturbance in the electric and magnetic field, which causes an electromagnetic wave to oscillate outwards like this. When it arrives here, electrons in the aerial will vibrate up and down as the wave passes through, and so the same frequency that was transmitted from here will be received here, and the radio will convert that electric signal back into a sound in the speakers. Okay. All types of electromagnetic radiation are the same apart from their frequency, and therefore their wavelength. Because the speed is constant, we have 3.0 times 10 to the 8, this is in a vacuum, is equal to frequency times wavelength. So in other words, if we increase the frequency, then the wavelength has to decrease in order for this to remain 3 times 10 to the power of 8. Alright. And here's a chart that kind of lists the different types of electromagnetic radiation. We have radio waves here at the long wavelength end of the spectrum. So here, let's do that. Here we have radio waves, which can be upwards of a kilometer. So that's 10 to the 3, that's 1,000 meters. And so we call long electromagnetic waves radio waves. When we get down to kind of centimeters here, those are called microwaves, which is what we use in the microwave oven or in a radar. Shorter still, and we're infrared, which we kind of can detect, not as light, but we detect it as heat. So if you sit under a radiating heater, for example, you can feel the infrared waves hitting you. So that's in the order of about 10 micrometers here. And then the visible range here is only a tiny little part of the spectrum. So our eyes are only sensitive to a tiny little bit of the spectrum, which is in the order of sort of hundreds of nanometers, or sort of a tenth of a millionth of a meter. And then we get shorter, and we have ultraviolet, which is kind of beyond violet, so we can't see it anymore. And those we've heard about because they can potentially be harmful to our skin. Soft X-rays and hard X-rays are used in medical procedures, amongst other things. And gamma rays are produced by nuclear decay, or nuclear kind of reactions. So that's the electromagnetic spectrum. And that's the pre-test. If anything that I've said is unclear, or if this stuff doesn't make sense to you, then make sure you note down the questions and ask.